The third major category of reactions occurring in the reactor is that of paraffin isomerization. This reaction is fairly slow and almost athermic. It does not produce hydrogen, but does not consume hydrogen either. However, it does make a significant contribution to the octane number. For example, the isomerization reaction of N-heptane into 2,2-dimethylpentane helps to increase the RON from 0 to 92. That means plus 92 points. As regards volume, this is a reverse effect compared to the two previous reactions. In fact, the isomerization of N-heptane into 2,2-dimethylpentane reduces the density by 9%. Transformation of 1 kg of N-heptane into 1 kg of 2,2-dimethylpentane increases the volume by 9% through a density effect. Here, there is no effect of change in mass as the reaction doesn't produce any hydrogen. There is one more major category of reactions that occur in the reactor. This is the cracking reaction. Cracking is the reaction occurring when a molecule in the hydrocarbon field divides into two lighter molecules. These reactions are slow, exothermic, and are enhanced at high pressures and temperatures. They also contribute to increasing the RON. This reaction of cracking of N-heptane to form N-hexane increases the RON from 0 to 25. Let's have a closer look at the impact on the volume. A kilogram of N-heptane represents 146 liters at 15 degrees C, which will convert to 1.86 kilograms of N-hexane, the rest being the methane formed. Even if the density of the N-hexane is less than the one of the N-heptane, the effect of the loss of mass by formation of methane is ultimately the stronger. Only 1.31 liters of N-hexane is produced, meaning a 10% loss in volume. It should be noted that these reactions reduce the reformate yield. Light molecules are produced as methane and ethane, ultimately as fuel gas, and consume hydrogen, unlike the reactions that we saw previously. In fact, all these reactions involve coke formation. As we get further into the cycle and as the catalyst will produce aromatics, these may polycondense on the surface of the catalyst and form coke. This phenomenon is accelerated if the temperature is very high and/or if the feed is heavier. The coke content of the catalyst is in fact measured during the cycle. So, here is the sequence of reactions that occur in the reactors. Naphthalene dehydrogenation and dehydrocyclization of paraffins that are very endothermic. The first three reactions are balanced, unlike the cracking reactions. We have also seen the reactions that produce hydrogen and those that consume hydrogen. Fortunately, at the end of the day, the balance is clearly on the side of hydrogen production. A typical value from hydrogen production is approximately 1.5 to 2.5 weight% of feed. The following graph gives an idea of how the octane number and the temperature evolve in the reactors. In the first reactor, a temperature drop of several dozen degrees occurs. This is the signature of naphthalene dehydrogenation. And we gain approximately 50% of the total octane number increase generated by the process in the first reactor. In the second reactor, the temperature drop is less and the octane gain is also lower. Finally, the last 10 to 15% of the octane gain are achieved in the last reactor, which usually has a catalytic volume corresponding to approximately 50% of the total catalyst inventory. This is needed to deal with the slow nature of the final reactions and to attempt to convert the remaining paraffins. So, what type of catalyst do we use in the reactor? In fact, we use a catalyst known as a bifunctional catalyst. The point is to have a hydrogenation dehydrogenation function and also an isomerization function. The hydrogenation dehydrogenation function is provided by the metal, while the isomerization function is provided by an acid group. The active elements are made up of one or several metals, including platinum, with a typical content of about 0.3% by weight on the catalyst. The catalyst will be made by extrusion, producing small sticks of 1 to 2 millimeters in diameter. In order to maintain catalytic activity, it is necessary to constantly inject chlorine into the feed to ensure the acid function of the catalyst. The optimum acidity is obtained when the water content in the recycled gas is between 15 to 25 ppm. This is why water is also injected into the feed to ensure that the acidity is kept at the optimum value. Once the naphtha has been converted and the effluent from the reactor has been cooled down in one or more heat exchangers, then in an ultimate air cooling unit, the hydrogen-rich gas is separated from the converted liquid. Part of the recycled gas is recycled and then to the fresh feed via a recycled gas compressor. Usually, the hydrogen-rich gas and the liquid reformate are put together to recover the LPG and obtain a hydrogenated gas that will be richer in hydrogen. Then, the converted feed, which still contains some LPG, is sent to a debutanizer. The function of this column is to separate what is known as the total reformate from the LPGs. Now that we have seen what the process looks like, we can look at the operating variables of the unit. So, we will meet again in the third and last part of this MOOC dedicated to catalytic reformer units. Thank you very much for your attention and see you very soon in the last part.